Section 7.3, Bonding in Metals. Here's our objectives. Model the valence electrons of metal atoms, describe the arrangement of atoms in a metal, and explain the importance of atoms. Okay, in a metal, the electrons kind of are shared in what they call this sea of electrons. So kind of think of it, let's say that we had a bunch of, that's the nucleus of an atom, and let's say this is iron or something like that. And normally you think of all these electrons kind of going around those atoms themselves. But what kind of really happens is that electron kind of just goes anywhere it wants to. And that's what they mean by a sea of electrons, is that electron can be anywhere, or it's shared between all of these metals, all of these that are in there. So they have what they call that free-floating valence electrons. They're just kind of free to move and do what they want. These moving electrons kind of create this force of attraction that holds these things together. So that's how these metals are kind of held together, by these moving electrons as they go through. Because these electrons can move, metals are really good conductors of electricity. Because, you know, if you've got this bar and you've got this electron that comes in here, on that side there's another electron that leaves here, and it just kind of takes the place. It doesn't really care. They share these electrons and they move around. There's not like particular for each particular one. Metals are also ductile, which means that you can pull them into air. They're malleable. You can kind of pound them into sheets. And the reason that they can do this is, once again, these valence electrons, they kind of shield each other. Look at this picture here. Alright, so first of all, you're seeing that it can be pulled through into a wire and it doesn't break. Now, if you try to doing that with a non-metal, it's going to break in there. And the reason that this happens is, if you take a look at this first picture, they're showing you that they're applying a force here, and these things move. But these negative electrons in there, they kind of cushion it. They kind of act like ball bearings, so that the positives, you know, the protons and stuff, they don't really get exposed next to each other and break or shatter. Whereas if you look at the second example, what happens in a non-metal, because they're locked in and you've got positives and negatives and so on, or in an ionic compound, I guess would probably be better, you get these negatives that line up and these positives that line up. And when that happens, that's a very strong force to break them away. In a metal, you don't get the positives and the negatives to line up like that and then force them. Metals usually arrange themselves in as tight a way as they can. They're usually very compact, usually very orderly. And there's three main types we're going to talk about, and I'll show you some pictures of these here in a little bit. But there's ones that are body-centered, and these have 8 neighbors. Examples of those would be like sodium, potassium, iron, chromium. We've got ones called face-centered, and these have 12 neighbors around them. Copper, silver, gold, aluminum, lead would be examples of those. And you have ones that are called hexagonal close-packed, which also have 12. And examples would be like magnesium, zinc, cadmium. Now let's see what those look like. Alright, so here's the first one. It says body-centered cubic. Notice that you've got like the one in here in the middle, and then you've got 4 of them up above it and 4 of them down below it. That's what they talk about by body-centered. Face-centered, you know, you can see that this is arranged a little bit differently. You don't have like one in the middle. You kind of have like, I mean, if you kind of looked at this layer here, you've got like 5, and then you've got 4, and then you've got 5 is kind of how it goes if you're kind of going from the one closest to us to the ones going to the back. And then you have hexagonal close packed, and you can kind of see how those are, you know, they've got hexagons and they've got a triangle kind of in the middle, you know, so there's my triangle. And then you got another set of hexagons at the top, and so on. So those are kind of just different arrangements. Just think about if you had a box full of balls, you know, you can arrange them in a number of different ways, depending on the size, depending on different things. You could make some different arrangements with them, and that's what these are. That's what we're talking about here. Most important things about metals is their ability to form alloys. So an alloy is really a mixture. It's not a compound of two metals, it's a mixture. In fact, it doesn't even have to be two metals. It has to be at least one metal and something else mixed together. But when you do that, you usually get better components, better properties than what you had with the original elements. So maybe you want to create something that is stronger. Maybe you want to create something that's more flexible, you know. So you mix certain different things together and you get those. Now, probably the most common alloy is steel. And steel is simply iron with carbon in it. And the more carbon you put in it, the more less flexible, I guess, it is. The more rigid the iron or the steel becomes. And so you just depend on, you know, however rigid you want that steel, you adjust how much carbon you put in there. So alloys are very important things because, you know, they give us better things. If you just had buildings made out of iron, they wouldn't be very strong. But when you make them out of steel, much stronger. Now there's two ways that alloys form. The first one is what they call substitutional. So think of if I had this package of, you know, tennis balls or something, and then I come and I take one of those out. So I take one of these out and I take one of those out, and then I come back and I put in a different one in between. That's substitutional alloys. That's what they mean by substitutional. And interstitial means that they fit together. So in substitutional, you would have, like, if you had balls that are similar size, like tennis balls and baseballs, you would get substitutional alloys. So when the atoms are similar sized, you get those types of alloys. If one is considerably bigger than the other one, then you get these interstitial alloys where the one fills in the gaps of the other one. Think about if you had a box full of ping pong balls and then you dumped in a bunch of BBs. You know, they're not going to take the place of the ping pong balls. They're just going to fit in the cracks in between them. So that's what an interstitial alloy is. That is the end.